Welcome back to the Deep Dive, where we take some of the most advanced, really mind-bending concepts in modern physics and try to distill them into something we can all understand.
And today we have a big one.
We really do. Today, we are wrestling with a concept that fundamentally challenges, well, everything you think you know about physical reality. The holographic principle.
It is, without a doubt, one of the wildest ideas to come out of theoretical physics. It suggests that the three-dimensional space we inhabit, our entire universe, might not be as real as we perceive it.
Right, so our mission for this deep dive is to unpack that, to really get our heads around this radical idea.
We need to trace it from the beginning. It has these really surprising origins in, of all places, black hole physics.
And from there, we'll follow it through the information revolution in physics, see how it became this incredibly powerful mathematical tool.
And finally, we'll look at where researchers are today. Are they actually trying to test if our reality is some kind of cosmic illusion?
Okay, so this isn't just an analogy, like a fun little thought experiment.
Not at all. The holographic principle is it's a supposed property of quantum gravity. It's a core feature of string theories.
And at its heart, it says what? That a 3D volume of space
can be fully, and I mean completely, encoded on its boundary. A lower dimensional surface, like a 2D gravitational horizon. It's like gravity itself demands this incredible economy of information.
There's a quote that always comes up here, the one from Leonard Susskind, that just perfectly captures how audacious this is.
Oh, I know the one.
He said, "The three-dimensional world of ordinary experience is a hologram, an image of reality coded on a distant two-dimensional surface."
Right.
So when he says that, is he just saying that, depth is just something our brains invent? Right. Or is it literally, mathematically not fundamental?
He's implying the latter. Absolutely. At the most fundamental level, the degrees of freedom, the bits of information you need to describe the universe, they don't scale with volume, they scale with area.
So the third dimension, depth.
It's an emergent illusion. It's a really effective one, but it's not primary. It's how our minds process this incredibly dense information that's actually living on a 2D boundary.
That is a serious claim. And it didn't just appear out of nowhere. It came from people like Gerard Hooft back in '93, right?
That's right. First, Hooft really laid the groundwork. He saw it as a necessary requirement for any workable theory of quantum gravity. And then Susskind came along and gave it its very precise string-theoretic meaning.
Building on even earlier work.
Exactly. Synthesizing Hooft's ideas with some really technical observations from Charles Thorne way back in 1978. So this has been brewing for decades.
So for you, listening to this, the reason this matters is that it completely redefines the basic building blocks of the cosmos. If this principle holds, then matter and energy, they're not the main show.
They become incidentals. That's the word Jacob Bekenstein used. They are incidentals to information. This was a huge shift, heavily influenced by John Archibald Wheeler.
Wheeler's famous it from bit.
It from bit. The physical world, the it, derives its entire existence from information, the bit. So if the universe is a hologram, its true reality isn't in its shape or its contents, but in the pattern of information written on its boundary.
Okay, let's start digging into that rabbit hole. Where did this all begin? This idea of encoding a 3D volume on a 2D surface. It must have come from somewhere concrete.
It did. It came directly from trying to figure out what happens to information when it gets near a black hole.
So, black hole thermodynamics.
Exactly that, and a concept called the Bekenstein bound. This was the unexpected spark that lit the whole fire.
Okay, set the stage for us. Before all this, what was the standard assumption in physics about information and space?
Well, normally, in classical physics, even in basic statistical mechanics, if you want to know the maximum information capacity of a region, what we call its entropy or disorder, it scales with the region's volume.
Which makes intuitive sense. Radius cubed. If I double the size of a box, I can fit way more stuff, way more information inside.
8 times more, right. That's the volume law. It's what we expect from living in a 3D world.
But Bekenstein found something different.
Something totally different, and it was all because of black holes. He made this incredible conjecture that the maximum entropy in any region of space, the Bekenstein bound, doesn't scale with volume. It scales with the radius squared.
The area.
The area. It's an area law, and that was just a radical departure. It means the information content of a system isn't limited by how big it is on the inside, but by the size of the surface that contains it.
So wait, if I have a giant warehouse The amount of stuff I can store isn't determined by the cubic footage inside, but just by the square footage of the walls.
That's the analogy. It's deeply counterintuitive. And the place where you see this law in action most clearly is a black hole.
How so?
Bekenstein realized that all the information of everything that has ever fallen into a black hole, stars, gas, planets, all of it, is somehow contained or encoded in the surface fluctuations of its event horizon.
And the event horizon is a two-dimensional boundary.
Fundamentally, yes. A 2D surface holding all the 3D information.
Okay, and this insight wasn't just a clever idea. It was a necessary fix for a huge, catastrophic problem in physics.
A huge one.
Because originally black holes were thought to have zero entropy, right?
That's right. In Einstein's theory of general relativity, they're perfect, simple objects. They're described by just 3 numbers: mass, charge, and spin. No internal randomness, no complexity. So, zero entropy.
And that puts you on a collision course with the second law of thermodynamics.
The most reliable law in all of physics, yeah. The law that says entropy or disorder in a closed system must always increase.
So you take a hot cloud of gas, something with very high entropy, and you throw it into a black hole.
Poof! Once it crosses the event horizon, all that information, all that randomness just vanishes from our universe. The black hole settles down and its 3 numbers change a little, but that's it. If the black hole itself has zero entropy, then the total entropy of the universe has just gone down.
Which can't happen.
Which can happen. It would shatter the second law.
So the only way out is to say that black holes aren't simple objects at all. They must be incredibly random. They have to have entropy.
And that entropy has to increase by an amount that's at least as much as the entropy of the gas you threw in. This is where the big theoretical debates really started.
Bekenstein proposed this, but Stephen Hawking was against it at first, wasn't he?
Very much so. Hawking had actually proved something called the area theorem, which states that the total surface area of a collection of black holes can never decrease. He even called it the second law of black hole thermodynamics.
But he thought it was just an analogy.
He did. He resisted the idea of it being real entropy, because if a black hole has entropy, it must have a temperature. And if it has a temperature, it has to radiate energy.
And nothing escapes a black hole.
Classically, no. So he argued they must have zero temperature and therefore zero entropy. He thought Bekenstein had it wrong.
But then, his own calculations, bringing quantum mechanics into the picture, forced him to change his mind.
Completely. He did a careful analysis of quantum fields near an event horizon and made his most famous discovery. Black holes do radiate.
Hawking radiation.
Hawking radiation, this slow thermal leakage of energy. So if they radiate, they must have a temperature. And if they have a temperature, they must have an entropy. Bekenstein was right all along.
And Hawking then came up with the precise formula, didn't he? The one that connects gravity, quantum mechanics, and thermodynamics.
He did. He fixed the exact number, the constant of proportionality. Black hole entropy is precisely 1/4 of its horizon area, measured in Planck units.
The Hawking-Bekenstein formula.
That's the one. It's this beautiful, profound connection. The number of microstates, which is really the total information content, is proportional to the area, A, not the volume inside.
Let's talk about those Planck units for a second. When you say A divided by 4 in Planck units, what does that actually tell us?
It tells us about the granularity of reality itself. The Planck length is the tiniest meaningful unit of distance, about 10 to the minus 35 meters. When you measure the horizon's area in those tiny little squares, it turns out that every 4 Planck squares can hold exactly 1 bit of information.
So the event horizon is like the universe's ultimate hard drive with a fixed information density.
Yeah, perfect analogy. And that area law is the absolute foundation of the holographic principle.
But this isn't a completely settled issue. I mean, you mentioned these things called Wheeler's bags of gold.
Right. It's important to mention the caveats. These are theoretical solutions in classical general relativity. They are configurations where you could, in theory, pack more entropy into a region than its surface area should allow.
So they would violate the Bekenstein bound.
If they could exist, yes.
So why don't they break the whole theory?
Well, the consensus among physicists is that these are artifacts of the classical theory. The belief is that a full theory of quantum gravity, the very theory where the holographic principle must operate, would simply forbid these solutions. They'd be unstable or impossible to form.
So their existence in the classical theory actually reinforces that the area law is a feature of quantum spacetime.
Precisely. The holographic principle acts as a kind of filter. Any successful theory of quantum gravity must naturally get rid of things like bags of gold. It's a key requirement.
Okay, so we've established the black hole's surface as this amazing information storage device. Now let's make the leap from a single black hole to the entire universe.
This is the big pivot. If we take this area law seriously, it forces a massive shift in our worldview. We have to stop thinking of the universe as being made of stuff, matter, and energy, and start seeing it as being made of information.
And you mentioned this is where Bekenstein was really pushing things, connecting physics to, well, to computer science almost.
He was. He keyed in on this incredible, unexpected connection between two different definitions of entropy.
A tale of two entropy.
A tale of two entropies. First, you have thermodynamic entropy. From Ludwig Boltzmann in 1877, this is what physicists use to measure disorder. Really, it's a count of all the possible microscopic states the particles in a system could be in.
So for a box of gas, it's the number of ways you could arrange all those atoms.
Exactly, a measure of complexity. Then, almost a century later, you get Shannon entropy.
From Claude Shannon, the father of information theory.
Right, and this has nothing to do with hot gas. This is about data. It's an objective measure of the information content of a message, measured in bits. It's what's used in your phone, on your hard drive, everywhere.
And what's so amazing is that these two ideas, born in completely different fields, turned out to have the same mathematical form.
Identical. Shannon's formula for the uncertainty in a message looked just like Boltzmann's formula for the disorder in gas. And Bekenstein said, this is not a coincidence. They are conceptually equivalent.
So the number of ways you can arrange particles, Boltzmann's entropy, is directly related to the amount of information in bits you'd need to describe that arrangement.
That's it. The only real difference is the units. One is in energy per temperature, the other is in dimensionless bits, but they're measuring the same fundamental thing, complexity.
And once you establish that equivalence, information and physical reality become deeply intertwined.
They become the same thing. Information becomes the most fundamental ingredient. Matter and energy are just how that information is manifested to us.
Which means the holographic principle becomes a universal statement. We take what we learn from black holes.
And we generalize it. We say the entropy of any region of space, not just a black hole, is ultimately limited by its surface area, not its volume.
Which leads to the unavoidable conclusion that volume itself, the 3D space we move through, is somehow an illusion.
It's an emergent phenomenon, a projection. The correct term is that the universe is isomorphic to the information on its boundary.
Isomorphic, meaning a perfect one-to-one mapping.
Yes. Every single thing that can happen inside the 3D volume is perfectly and completely described by the physics happening on that 2D surface. The depth we experience is just a consequence of how that boundary information is organized.
It's like the universe is a book, and we're experiencing the story, but the fundamental reality is just the ink on the page.
A great way to put it. And that page, that boundary, isn't some wall you can fly to. It could be the boundary of the universe at infinity. The point is, the complexity, the degrees of freedom grows with area, not volume.
Okay, a claim as huge as volume is an illusion needs some serious mathematical backup. We can't just leave it as a concept. Is there a working model where this actually happens?
There is, and it's the most rigorous, most successful realization of the principle we have. It's called the ADI-CFT correspondence.
The anti-de Sitter conformal field theory correspondence, also known as the Maldacena duality.
That's the one. It is the concrete mathematical proof that, yes, a theory with gravity in a higher dimensional volume can be exactly equivalent to a quantum theory without gravity living on the boundary of that volume.
Let's break that down, the two sides of it. First, the bulk side. Anti-de Sitter space, or ADS. What is that?
ADS is a specific kind of space-time geometry. The key thing is that it has a negative cosmological constant.
Unlike our universe, which seems to have a small positive one.
Right. Our universe is expanding and accelerating. ADS space sort of curves back on itself, and, crucially, it has a boundary at infinity. That boundary is absolutely essential because that's where the other side of the duality, the CFT, lives.
So the ADS space is the higher dimensional volume that contains gravity and string theory.
Yes, that's the bulk.
And on its boundary lives the CFT, conformal field theory. What's a CFT?
A conformal field theory is a type of quantum field theory that has a special kind of symmetry. It looks the same at all scales. If you zoom in or zoom out, the physics doesn't change.
And these are theories we understand pretty well.
Very well. They're like the Yang-Mills theories that describe the elementary particles in the Standard Model. They describe physics without gravity.
So the duality, the correspondence, says that these two completely different looking universes, one with gravity and strings in, say, 5 dimensions, and one with just quantum particle physics in 4 dimensions.
Are mathematically identical. They are two different languages describing the exact same physical reality.
What makes this so incredibly powerful for physicists?
It's what we call a strong-weak duality. And this is the magic trick.
Okay.
In physics, things get really, really hard to calculate when forces are strong. Think of the strong nuclear force that holds quarks together inside a proton. The math just breaks down.
Right, you can't just make small corrections. The interactions are too chaotic.
Exactly. It's mathematically intractable. But here's the amazing part of ADS-CFT. When the physics on the boundary CFT side is strongly interacting and impossible to solve, the physics on the gravity ADS side becomes weakly interacting and simple to solve. You can use the classical equations of general relativity, basically.
Wait, so you're telling me you can take an impossible problem in quantum physics, translate it into a simple gravity problem in a higher dimension, solve it there, and then translate the answer back?
That is exactly what it is. It's like a universal mathematical cheat code.
Give me an example.
The quark-gluon plasma. This is the stuff that filled the universe for the first few microseconds after the Big Bang. It's a soup of quarks and gluons, and it's incredibly strongly interacting.
Impossible to calculate its properties from first principles.
Almost. But using ADS-CFT, physicists translated that problem. The strongly coupled plasma became equivalent to a simple, classical black hole living in the 5D ADS bulk.
A black hole represents the quark-gluon plasma.
It does, and they could easily calculate the properties of that black hole, like how it absorbs energy. This gave them a prediction for the viscosity of the plasma, how easily it flows.
And what happened when they did the experiment? At places like the relativistic Heavy Ion Collider.
The results were a stunning confirmation. They created the quark-gluon plasma, and it behaved like a near-perfect fluid with incredibly low viscosity, a value that matched the prediction from the black hole calculation almost perfectly.
Wow. So it actually works. It makes real-world, testable predictions.
It does, which is why Maldaceno's 1997 paper on this became the most cited paper in the history of high-energy physics. It gave physicists a brand new, powerful toolkit.
And this idea wasn't entirely new, was it? Brown and Eno had a precursor to this.
They did. Back in 1986, they showed that gravity in a 2+1-dimensional ADS space was equivalent to a 2-dimensional CFT. So they proved the concept was possible long before the full correspondence was worked out.
Okay, so we have the theory, we have the mathematical model. Let's circle back to the problem that started it all. The black hole information paradox.
Right.
How does the holographic principle actually solve it? What happens to the information?
So the paradox, just to recap, was that Hawking's original calculation suggested that the information of whatever falls into a black hole is permanently destroyed when the black hole evaporates.
A violation of quantum mechanics.
A huge one. Quantum mechanics says information can never be truly lost. So for decades, physicists were stuck.
And Susskind, using holography, came up with the answer.
He did. He argued that the information isn't lost because it never truly makes it inside in the way we think. The infalling matter leaves an imprint, an engraving of its information, on the furiously vibrating 2D event horizon.
So the horizon isn't a passive boundary. It's a scrambling device.
A quantum scrambling device. It takes the information, scrambles it completely, and then slowly re-emits it as subtle correlations within the outgoing Hawking radiation.
So the information gets out, it's just incredibly hard to decode.
Exactly. The total quantum state is preserved, information is safe, and the holographic resolution is that the 3D interior we imagine is just an effective description. The real physics, the fundamental degrees of freedom, are on that 2D horizon.
And this idea that information has a maximum density, the Wittgenstein bound, it has other huge implications, doesn't it, for the very structure of matter?
It does. If any finite volume can only hold a finite amount of information, that puts a hard limit on how complex things can be.
So in classical physics, you could just keep dividing matter up forever.
Yeah.
A particle could have infinite internal parts.
Infinitely. But if that were true, a single particle could contain an infinite amount of information. And if you put it in a box, you would immediately violate the Wittgenstein bound. The box would collapse into a black hole.
So the holographic principle basically says that you can't divide matter forever. The subdivision has to stop somewhere.
It has to. It implies that reality is fundamentally granular. It has a minimum resolution. It has pixels, so to speak, at the Planck scale.
A pixelated universe.
Yeah.
That's a testable idea, isn't it? Has anyone actually tried to look for this cosmic pixelation?
Yes, there have been attempts. The most famous was probably by a physicist at Fermilab named Craig Hogan.
What was his idea?
He argued that if space-time is fundamentally pixelated or granular, it should lead to a kind of intrinsic jitteriness, a holographic noise. Tiny, random quantum fluctuations in the very position of things.
And he thought he could measure this.
He built an experiment called the holometer, a very sensitive interferometer, specifically designed to look for this tiny, correlated spatial fuzziness.
Did he find it?
He did not. The holometer didn't detect the noise he predicted. And to be fair, his specific predictions were controversial. Most string theorists argue that if this noise exists, it would be far, far smaller than what his experiment could detect.
And wasn't there an astronomical observation that also contradicted it?
There was, and it was a pretty strong blow. In 2011, scientists analyzed the light from a very distant gamma ray burst. The sharpness of the signal allowed them to put a very strict limit on any fuzziness of space-time. They found that space was smoothed down to a scale of 10 to the minus 48 meters, which is vastly smaller than the scale Hogan was predicting. So that specific model of holographic noise seems to have been ruled out.
So where does the research go from here? If ADS-CFT is the gold standard, but our universe isn't ADS space.
That's the frontier. The cutting edge of research is trying to move beyond ADS space. This has led to a new subfield called celestial holography.
Trying to build a hologram for our actual universe.
That's the goal. Our universe is what we call asymptotically flat. It's not closed like ADS. So researchers like Andrew Strominger at Harvard are trying to figure out how to formulate a holographic duality for our kind of space-time.
And where would the lower dimensional hologram live in this case?
The idea is that it lives on the celestial sphere. This is a mathematical sphere at the infinite future boundary of our space-time, where light rays end their journey.
So the entire history of our 4D universe could be encoded on a 2D sphere in the far, far future.
That's the conjecture, and they're trying to make this testable. The idea is that the underlying symmetries of this 2D celestial theory should leave imprints on things we can observe today.
Like what?
Specifically in the patterns of very low-energy particles, like soft gravitons and soft photons. The dream is that we might one day be able to see the signatures of the celestial hologram in the fine details of gravitational waves detected by observatories like LIGO or LISA.
So this is moving from pure theory to something that could one day be observational science.
That's the hope. It's an attempt to take the profound lessons we learned from black holes and apply them to the entire cosmos we live in.
What a journey. I mean, we started with this strange little puzzle about black holes.
That their information content was written on their surface, not stored in their volume.
And that one idea, that area law, snowballed into the holographic principle, which suggests that the third dimension itself might be an emergent illusion.
We then saw how this was given a rock-solid mathematical foundation with the ADS-CFT correspondence, this incredible tool that lets us solve some of the hardest problems in physics.
And now, the quest is on, with things like celestial holography, to see if we can actually prove that our universe, the 4 dimensions we experience, is just a projection of information written on a boundary we can't even see.
You know, if you really take a step back, the biggest takeaway from the holographic principle is that the universe isn't defined by its physical contents. It's not about the matter or the energy. It's about the information it contains, the bit that creates the it.
Which leaves a pretty profound final thought.
It does. If the volume is illusory and all the information is really encoded on some distant boundary, then what is the true nature of that boundary? Is it just a mathematical convenience? Or is that boundary where the fundamental, irreducible reality of our universe actually resides?
Something to think about the next time you look up at the night sky. Thank you for taking this deep dive with us. We'll see you next time.